Let's go over homework 6 using Microsoft Excel. This is kind of a quick and dirty way to get some important parameters pertaining to enzyme kinetics. And remember, the two most important variables with regards to enzyme kinetics, specifically Michaelis-Menten kinetics, are Vmax and Km. So there's usually more expensive softwares, very specialized softwares dealing with kinetics. But there's also some tricks you can use with Microsoft Excel to get the same parameters. The only disadvantage with Microsoft Excel is that it does not do any type of fitting. Fitting is very important in enzyme kinetics, and more specialized softwares can deal with that. So let's deal with homework 6, problem number 1. Here we're given a list of substrate concentrations and initial velocities of substrate being turned over to product. So let's just copy this and Control-C. Let's paste this into a fresh Microsoft Excel document, as I have done here. And let's just expand the width of each of these cells. The Michaelis-Menten plot is a plot of the velocity on the y-axis and the substrate concentration on the x-axis. So what we can do is highlight this, and in Microsoft Excel, go to Insert. I like to use scatter plots, and you can see the scatter plot happens automatically. Sometimes you just want to connect the dots, so click on an individual dot, change series chart type, and we can connect them also. So whether you want to connect or leave the as an individual scatter plot, I'll leave that up to you. It's very important that when you work with any type of graph that you label the axes. So this is so crucial and so important that it's you just have to do it. So in order to do that in Microsoft Excel, what we can do is under the Design tab, you go to Add Chart Element. We'll add an axis title, a primary horizontal. And remember, in the Michaelis-Menten plot, the x-axis is always going to be the substrate concentration. So I'll put substrate here. And in our y-axis, we go under the Design tab, make sure it's highlighted, Add Chart Element, we go to Axis Title, the primary vertical axis, and this one is going to be VO. And I'll put the units here of millimeter per second. So our axes are labeled. In some cases, we can also employ a chart title. So make sure your Design tab is highlighted under Chart Tools, Add Chart Elements. We'll put a chart title, and we'll call this the Michaelis-Menten plot. We don't get a lot of information from the Michaelis-Menten plot, other than it does follow Michaelis-Menten kinetics. How do I know? Because of that hyperbolic shape. That hyperbolic shape is indicative of Michaelis-Menten kinetics. Notice that if we continue to persist the substrate concentration ad infinitum, the initial velocity of the enzyme catalyzed reaction, it will eventually plateau. So essentially, we're saturating all the active sites in the enzyme. This really doesn't give you much information on Vmax in case of M. We can extrapolate case of M from the Michaelis-Menten plots. More expensive softwares can actually do that. But another way you could do this is through the Lineweaver-Burk plot or the double reciprocal plot. So the double reciprocal plot is 1 over substrate on the x-axis and 1 over the reaction velocity on the y-axis. So let's create another column here, and we'll call that 1 over substrate, 1 over the concentration of substrate. And we'll do the equal sign to set up an equation, 1 divided by, and the cell in A2, hit enter, and that is 1 over 0.02. We can click on that cell and drag it all the way down. We'll do the same thing for 1 over V sub O. Notice the units now have flipped. Now it's seconds over millimolar. Here we do an equal sign, 1 divided by the contents of the cell in B2. Click that, see that little corner square, make sure the cursor changes, and then we can drag this all the way down. So now what we can do is plot, instead of VO versus substrate, we'll plot 1 over VO versus 1 over substrate. So there's several ways to do that. We can start, as we've done before, and highlight and go to Insert. And we always label the axes. So label the axis under Design, Add Chart Element, Axis Titles. The horizontal axis is now going to be 1 over the substrate concentration. And click on the y-axis, Add Chart Element. The primary vertical axis label is 1 over v sub naught, or 1 over the initial velocity. I'll put the units here. It's going to be seconds. Seconds divided by millimolar. Okay, millimolar is what that term is. And this is the Lineweaver-Burk plot. So let me expand on this. Notice that in the Lineweaver-Burk plot, what we have learned in class is where this line hits the y-axis, or the y-intercept, that is 1 over Vmax. And where this line hits the x-axis, or the x-intercept, is minus 1 over Km. Now, the problem, because this is Excel and this is a quick and dirty method to get Km and Vmax, we have to do a little bit of extra work. One thing we can do is extend the axes. So if we click on the x-axis and let's change the bounds from the minimum on the x-axis is 0. We want this graph to go to the point where it hits the negative x-axis. So I'll try -5. And we can even go to -10, but that should be okay. All right. So now we want the point where it hits the y-axis, and then we want to extrapolate it where it hits to the minus x-axis. So actually, I will not go to -5, but I'll go to -15. Okay, that's a little bit better. Right. So where will it hit the y-axis and where will it hit the x-axis? So in more sophisticated softwares, it will be automatic. We got to do a couple of extra steps here in Excel. So first of all, we'll click on those points, right-click, and go to Add Trendline. And we want to fit it to a linear equation. Remember, the double reciprocal plot will be a line with slope y with an equation y equals mx plus b. It's very important that we display the equation on the chart and we display the r-square value. The r-square value gives us information on how close to linearity this graph is. With an r-square of 1, that is very, very close to linearity. So now we have everything that we need to get Km and Vmax. Unfortunately, in Excel, you cannot draw or extend that line to the y-intercept and to the x-intercept. So visually, that is cannot happen. But we can still get the y and x-intercept mathematically, and let's do that now. So as we stated before, the y-intercept, 1 over Vmax. So the y-intercept is when the x value is equal to 0. So when your x is equal to 0, what is your y? It's going to be 0.0154. So when x is 0, y is 0.0154. That is 1 over Vmax. So what will Vmax be? Vmax will be the reciprocal of that, so equals 1 divided by this would be 64.9. Don't forget your units, millimolar per second. I'll just highlight this with yellow, maybe red text. What about the x-intercept? Okay, the x-intercept is where this line, when we extrapolate it, hits the x-axis. And at that point where it hits the x-axis, y is 0. So when y is 0, we will solve for x. And in that case, x is going to equal to minus 0.0154 divided by 0.0015. So equals minus 0.0154 divided by 0.0015, and we get minus 10.26 is the value of x, but that is minus 1 over km. To get k sub m, we take the negative reciprocal of that. So we will take the negative reciprocal of that because, as we stated before, km cannot be a negative value. Km is a substrate concentration where V is equal to V max over 2. Once again, Km is a substrate concentration where V is equal to V max over 2. So we have to take the negative reciprocal of this. So equals minus 1 divided by what's in the cell. And it's going to be 0.097. The units here are going to be in millimolar. So we can highlight that and paint it red. Part D of this problem tells us to calculate the kcat and the catalytic efficiency. So the kcat is defined as Vmax over the total enzyme concentration. The total enzyme concentration, as we mentioned in class, was 2 millimolar. So from there we can be able to calculate Vmax over total enzyme concentration, which is kcat. So our Vmax is 64.935 divided by 2. The millimolars cancel, and we get 32.46. The units are seconds to the power of minus 1. So every second, this enzyme is turning over 32.46 molecules of substrate into product. That is essentially what kcat is, also known as the kcat value. The catalytic efficiency is nothing more than kcat over km. So we have already calculated kcat from the previous problem, and km we got from the Lineweaver-Burk plot, and it's 333. Taking care of units, the units of kcat is seconds to the minus 1. The units of km, remember, it's a substrate concentration, so the units of that are going to be in millimolar. So kcat over km will be 333 seconds to the minus 1 and millimolar to the minus 1. Taking a look at homework 6 problem number 2, here is an enzyme kinetics problem that has a direct relationship to cancer therapy. So let's figure out Vmax and Km with the inhibitor and without the inhibitor, and let's determine the type of inhibition that sphingosine actually is. So let's just copy and paste this table here to the second tab of homework 6. Let's extend the width of our cells just for our ease and comfort. So let's first do a Michaelis-Menten plot. So that's going to be substrate on the x-axis, which is sphingosine on the y-axis. Let's first do it without the inhibitor. So we'll highlight this, and we'll insert. Let's insert a plot where we connect the dots, and there is what that would look like. Let me just put it down here, and let's label our axis here. This is Michaelis-Menten plots. Label our axes. It's worth taking the extra time to do that. Right, so that is without the inhibitor. Let's do it with the inhibitor as well. Maybe a good idea to get a legend, and so we'll put a legend here at the bottom. So this one is a legend without the inhibitor. So now let's plot it with the inhibitor. So in order for us to do that, we can click on this graph, right-click, select data. So we're adding a chart here, so we'll add. The series name will be the data with the inhibitor. The x values are going to be here. The y values are going to be the values with the inhibitor. And let's click OK, and OK again. Notice that my figure legend has been updated My axes have been properly labeled. And as expected, in the presence of an inhibitor, this Michaelis-Menten plot slopes downward. I could do the double reciprocal plot to determine the type of inhibition there is. So this would be 1 over the substrate. So 1 divided by sphingosine. And we'll do 1 divided by VO without the inhibitor. Without I, I'll call it. So equals 1 divided by no inhibitor. And then 1 divided by initial velocity with inhibitor. So now we have all our data. We're ready to plot. So what we can do is plot it as another graph, or what we can do is, now you can do it as we've done before. Here's another trick in Excel that you can do. You can copy and paste somewhere else the original chart that you've made, and we'll click on the blue. Blue is without the inhibitor. Substrate versus velocity without the inhibitor. So now let's just switch here to 1 over substrate and 1 over VO without the inhibitor. We'll change this header here also. And we'll do that for the orange graph as well. The orange graph, instead of being substrate, it's going to be 1 over substrate. And instead of velocity, it's going to be 1 over the velocity with the inhibitor. Make sure you drag this properly. So 1 over VO without inhibitor, 1 over VO with inhibitor. I got to change my axis labels. That's going to be very important. I'll even change my units here on the y-axis. So minutes per milligram. All right, here we go. Now with our Michaelis-Menten plot, or excuse me, our Lineweaver-Burk double reciprocal plot, we're able to determine Km and Vmax. So let's do Km and Vmax without inhibitor. And so let's click on the blue. The blue is without the inhibitor. Right click, add Trendline. We want to fit this to a line. And we also want to be able to display the equation and display the R value. And let's do it also for the orange curve. Add Trendline. Make sure it's linear. Display the equation and display the R square value. Let's extend the x-axis because we know that the x-intercept is going to intercept into the second quadrant. So we can format the axes and we'll make the bounds minus 0.5 maybe. Maybe that's a little bit too much. How about minus 0.2? Maybe a little bit better. All right, now we're ready to do our calculations without the inhibitor. So without the inhibitor, the Vmax is going to be where it's 1 over the Vmax here where it hits the y-axis. In other words, the Vmax is 1 over the y-intercept. So right where this blue line crosses the y-axis is 1 over Vmax. To get Vmax, we flip it or take the reciprocal. At this y-intercept, x is equal to 0. So when x is equal to 0, you get a value of 0.0081. And 1 over that will be our Vmax. And that's going to be 123.45. And we got to make sure our units are proper, milligrams per minute. So that is without the inhibitor. Let's do the same thing for Km. So Km, we're going to extend this blue line all the way till it hits to the x-axis, where it's going to be in the negative quadrant. At that point, the x value is going to be negative something, but our y value is 0. So we'll plug in 0 for here and solve for x. So in that particular case, we have x equals to minus 0.0081 divided by 0.058. And we're going to take the negative reciprocal of that. And we get 7.16. This is a substrate concentration. And the substrate concentration here for for this problem is in micromolar. All right, so here are two values of Vmax and Km. Let's just highlight that. Now let's do the exact situation with the inhibitor. So with the inhibitor, you notice we have this counterclockwise shift of the main line, and that means that inhibition has caused a change in the Vmax and Km. So now we have what's called the apparent Vmax and the apparent Km. So apparent max and Km apparent. So this orange line is with the inhibitor. Let's first do the point where it hits the y-axis, and that's where x is equal to 0, and y is going to be 0.0105. We take the reciprocal of that to get the Vmax, and we get a value of 95.2381 megs per minute. Where this line hits the x-axis, the negative x-axis is going to be minus 1 over Km. Take the negative reciprocal because Km, being a substrate concentration, can never be negative. And so plugging in y equals 0 here and solving for x, we get equals minus 0.015 divided by 0.271. And that's minus 0.3875. Take the negative reciprocal of it, and we get, make sure you take the negative reciprocal of it, and you get 25.805. So now we have an apparent Vmax, and we have an apparent Km. You don't forget the units here. The units here are going to be in micromolar for Km. So comparing Vmax and Km for situations with and without inhibition, we see that Vmax has gone down, and we see Km has gone up. So in what type of enzymatic inhibition do you see Vmax going down while Km also going up? Will it be competitive inhibition? Will it be non-competitive inhibition? Or would it be uncompetitive inhibition? Well, the answer to this is that it's going to be some sort of mixed inhibition. We really don't know. It doesn't seem like they're going to intercept at a common y-axis, in which case that would be a competitive inhibition, and it doesn't look like it's going to intersect at a common x-axis, where you would have perfect non-competitive inhibition. So the correct answer here is that we have mixed inhibition. We have a combination of this inhibitor inhibiting the enzyme, and a combination of this inhibitor inhibiting the enzyme substrate complex. So given the information that we have now, we can best surmise that this is a mixed inhibition. All right, homework 6, problem 3, very simple. We're just given a plain set of data, substrate and initial velocities. So we can copy and paste this, and we can very easily determine the Km and Vmax. So first, we'll do our Michaelis-Menten plot here, and you can see the hyperbolic shape. We will plot the labels. X-axis is going to be substrate, and y-axis is going to be your velocity. So correct labels on the axis, chart title, all of those are very important for getting a very good graph. Double reciprocal plot is going to be 1 over S, so equals 1 divided by this, and 1 divided by VO, initial velocity. And we can go ahead and plot that, highlight that, insert, and we will have that graph generated as a line. Once again, it's very critical that you label the correct axis labels. Click on the line and right-click, add Trendline, linear. You want to fit this to a line, y equals mx plus b, display the equation, display the r² value. We have our equation, we have all we need now to calculate Vmax and Km. With a straight enzyme problem, there is no inhibition. Vmax is where this is going to hit the y-axis, we take the reciprocal of that. Let me just extend the x-axis. So where this intersects the y-axis is where x is going to be 0, and y is going to be 0.83. That's 1 over Vmax, so Vmax is going to be 1 over that, and that's going to be 1.20 millimolar per second, excuse me. And then Km is where this is going to hit the negative x-axis, where y is 0. So y is equal to 0. And solve for x. X is going to be equal to minus 0.83 divided by 0.2111. We get that. Km is the negative reciprocal of that. Don't forget to make it a negative reciprocal. And we get 0.254. The units of the substrate concentration are in micromolar. So there you have it. Using Microsoft Excel, we're able to calculate Km and Vmax. Took a little bit more time than more sophisticated softwares, but we can solve the problems with an inhibitor and without an inhibitor and determine the type of inhibition. And we can also determine Kcat and catalytic efficiencies of the enzyme towards its substrate. Don't forget to always save. We'll move on to homework 7 problems in the next video.